Hello everyone, my name is HalilAkgul. I'm a freshman computer science student at Bilkent University. Today I will present my PHYS102 lab project, investigation of frequency response and resonance characteristics in series RLC circuits. The main objective of this experiment was to investigate the relationship between the resonance frequency and the fundamental components, inductance and capacitance, in a series arrangement. I also analyzed how total impedance and phase shift change with frequency, specifically focusing on the quality factor and energy dissipation. For the setup, I used a signal generator to provide a sinusoidal input, a digital oscilloscope to monitor the waveforms, and a breadboard with specific R, L, and C components. My procedure involved a frequency sweep from low to high frequencies while meticulously recording the resistor voltage and the time delay. I conducted the experiment in two parts, part A with a 100 ohm resistor and part B with a 1 ohm resistor, to observe the damping effects. In this part of the experiment, I focused on the frequency response of the circuit using a 100 ohm resistor. I started the experiment at a low frequency of 1 Hz and carefully observed both the input and output voltage signals on the oscilloscope. As I gradually increased the frequency, I meticulously recorded each value in the data table to map out of the circuit's behavior. Throughout the sweep, I monitored the amplitude of the output voltage. I specifically recorded the point where the output voltage reached its maximum and then suddenly began to drop. This critical point allowed me to identify the exact experimental resonance frequency for this setup. I repeated the same things for part 2 as well. After collecting the raw data from the oscilloscope, I performed the necessary calculations to prepare my data tables. Specifically, to find the RMS values of the voltages, I used the formula VPP, which is the peak-to-peak voltage. I measured it directly from the screen. By applying this formula to each measurement, I consistently filled out the data tables for both parts of the experiment. Next, I used these calculated values in Excel to plot the VR versus frequency graphs. These graphs are crucial for analyzing the bandwidth and selectivity of the circuit. In part B, with the 1 ohm resistor, I observed a very sharp and distinct resonance peak, indicating a high quality factor and narrow bandwidth. In contrast, for part A, with the 100 ohm resistor, the peak was significantly flatter and wider. This result perfectly aligns with the bandwidth theory, demonstrating that high resistance increases damping and broadens the frequency response. Finally, I conduct a thorough error analysis by comparing my experimental resonance frequency of 20.5 Hz with the theoretical value. By using the percentage error formula, I validated the accuracy of my setup. The minor discrepancies I encountered were meticulously analyzed and attributed to factors like the internal resistance of the inductor and component tolerances. In conclusion, this experiment successfully demonstrated the frequency response and resonance characteristics of a series RLC circuit. By analyzing our data, we observed that the resonance frequency occurred consistently around 20.5 Hz, where the circuit transitions from capacitive to inductive behavior. The phase shift measurement clearly confirmed the theory, as the phase angle dropped to zero at the resonance point, proving that the circuits behave as a purely resistive system at this frequency. Despite minor experimental errors, the strong correlation between our experimental findings and theoretical calculations validates the mathematical model of RLC oscillations. This experiment has provided a comprehensive understanding of how fundamental components interact in an AC circuit. Thank you for your time and thank you for watching my presentation.